Okay, now we're doing section 5-6, radical expressions. Sorry about my handwriting. Okay, here we go. This follows the worksheet that is attached to this post. Well, let's just get started. The first two examples is combining like terms, or adding, subtracting radical expressions. One of the basic skills you need to already know or already have is being able to simplify just single radicals. Like here, 2 root 20. You should already be able to simplify that kind of an expression. And then once you know how to do that, then this is the next step. Alright, so what we're going to do first is simplify 2 root 20. I'm going to do quite a bit of this in my head. I will show a couple steps. 20, normally we make a factor tree, is 2 times 2 times 5. So 5 cannot be factored any further, so we leave that alone. But here we have a pair of 2's that's going to come out and gets multiplied with the outside number. So it's 2 times the 2 coming out. Okay, let me say that again. So I have a pair of 2's that comes out as a single 2, and it's going to get multiplied with the coefficient. So that becomes 4 root 5 minus 3 root 5. Alright, so now we have 4 root 5 minus 3 root 5. One thing to note, you treat the radicals as if they were variables, meaning they have to be identical for you to combine like terms. So here, this is a square root of 2, this is a square root of 5, so these two cannot be combined. While these two, they both have a radical 5, can be combined. And all you're going to combine are the coefficients. So you're just going to do the 4 minus 3, which is 1. And we're not going to bother to write the 1. So the answer to the question is negative root 2 plus root 5. Number 3. It seems like I'm counting strangely. I'm only doing the odd problems from the worksheets. Alright. This one might be too easy. Well, here, we don't need to simplify anything. All we're going to do is combine like terms. 3 root 2 minus 3 root 2 is 0, which we're not going to bother to write. Final answer, negative 2 root 3. Maybe that was too easy. Hopefully 1 was enough. Alright, number 5. I generally like to simplify or reduce fractions first. In this case, I can simplify the square root of 4, making it 2 over square root of 5. And then I'm going to rationalize the denominator. What that means is I do not want the square root or any kind of radical in the denominator, and I want to get rid of the radical from the denominator. In order to do that, we have a technique called rationalizing the denominator. When we rationalize the denominator, we're going to do basically an algebraic trick. And we're going to multiply that number by a number that'll make it a perfect square. Well, the obvious choice is 5. And what we're going to do is multiply by square root of 5. But whatever we do to the denominator, we have to do to the numerator. So we multiply the numerator by square root of 5. Now, the 2 is not in a radical. 5 isn't a radical. Numbers outside and inside do not meet. They just combine like that. That's still read 2 times square root of 5. So essentially we just put them together and not do the actual multiplication. Alright, here, well, that's probably technically said wrong, but you get the idea. Alright, so square root of 5, square root of 5. When we multiply those, since they're both in the radical, we can combine them, making it square root of 25. And remember, the whole point was to get rid of the radical, so we shouldn't be surprised that that's a perfect square and square root of 25 is 5. In fact, in the future, I may skip this step and go straight to this one. Moving on to number 7. Number 7 is similar to number 5, so if you want to try it out before watching the video, copy the problem now and pause the video. Alright, here we go. Now, like I said earlier, that I like to reduce my fractions. Since they're both in a radical, I can actually reduce them. there is a common factor of 3 to both of them. So I can make a square root of 2 over square root of 5. Reducing now will save some headaches later. Okay, here we go. So here, I want to rationalize the denominator. It's 5 again. So I'm going to multiply top and bottom by square root of 5. That would make, since this time the 2 is under the radical, I can multiply the 2 into 5, making it square root of 10. Remember, the whole point of multiplying the denominator by square root of 5 is to make it a perfect square. So I'm going to skip the step where I write square root of 25 and simply write 5, because I know square root of 5 times square root of 5 makes 5. And that's the answer. Now I'm going to repeat number 7 just to show you what happens if you don't reduce first. Okay, so I'm repeating number 7, and I'm not going to reduce it to begin with, so which means I'm going to multiply by square root of 15 first. Alright, multiplying by square root of 15. Okay, so 6 times, so that's square root of 90 over 15. Now, 90 looks like it can be simplified. In fact, we'll go ahead and factor that. It's 3 times 3 times 2 times 5. I basically did the factor tree in my head. Alright. So I got a pair of 3's that's going to come out. And 2 and 5, there are no pairs of 2's or 5's. So they stay inside and they get multiplied together. And 15. We don't do anything. And here, we can reduce the 3 into 15, making it square root of 10 over 5. Okay. So we get the same answer, but notice the extra work. So it's better to go ahead and reduce at the beginning rather than wait for the end. Is it okay to wait for the end? Yes. Alright, but you see the difference in work. Number 9. Number 9 is actually rather similar, even though it might look a little different. Okay. Here, all I need to do is get rid of the square root of 11, so I don't need to worry about the 4. It's not in a radical, and I don't really need to do anything about it. But I do have to do something about the square root of 11. So I need to pick a number that would make that a perfect square. So I don't need to worry about the 4. So I'm going to multiply top and bottom by square root of 11. That's going to give me, here, 5 is not in a radical. So it just multiplies 5 root 11. This 5 is in the radical, so it multiplies 5 and 11, making it 55. Here, remember, square root of 11 times square root of 11 is 11. So it's 4 times 11 here. Making it 44. Check to see if this can be reduced or whatever. 55 came from 5 and 11. They're both prime numbers. They can't be factored any further. So there's no coefficient other than 1 in front of square root of 55. It means nothing can be reduced between numerator and denominator. So that's it. That's number 9. Number 11. Here, we're going to rationalize the denominator again. So I'm multiplying top and bottom by whatever makes the denominator a perfect square. In case, square root of 3. So, multiply 4 and root 3, making 4 root 3, minus 3, 5 times 3, square root of 15. Square root of 3 times square root of 3 is 3. 3 goes into that, but 3 won't go into the 4, so that cannot be simplified any further. And that's number 11. Okay, before I do number 13 through 19, I have to talk something about a conjugate. Okay, a conjugate